for the invitation, and this will be a talk on the hot probes. And my plan is to introduce you a bit on what is hot probes doing. It's a heavy on program and its sensitivity to initial conditions. And the second half of the talk will be a presentation of some of the work we have been doing during the workshop on the study of isobar related things. So that's my plan. Oh. All right, let's see, there's some delay. So what we mean by hot probes? When we do heavy ion collisions, this is a high energy collision. So from time to time, we not only produce the quark-gluon plasma, but also some hard scattering process with high momentum transfer can happen. And there are two types of probes we are interested: the colorless probes, which is very important and it can be used to detect the initial state of the scattering and also validation of our calculations. And the second part is the color probe. And those are fast-moving, high-energy quark and gluons, heavy quarks, and they can be used to study the medium properties. And just a quick introduction of the main physics observables we have been using for rebuilding the median effect in AA collision. So this is the nuclear modification factor, RAA. It's essentially the ratio of the QCD in median versus QCD in vacuum. If this factor is providing a fair comparison between PP reference and the AA measurements by scaling down the AA measurements by NCOL, which is the number of binary collisions in AA collision. If this number is 1, this means that there's no median effect. If RA is smaller than 1, this means that there's a suppression of the process of interest. With this in mind, we can first have a look at the colorless probe performance, and you can see from here the nuclear modification factor RAA is presented as a function of N part or in beams of centralities. Left-hand side is the Z boson, and you can see the RAA value is dancing around 1. And right-hand side shows you 1, 2, 3, 4 different centrality intervals. Those are the presentation of the photon RAA as a function of photon energy, and you can see the same picture there. So essentially what this shows us is that electroweak probes are essentially NCOL counting machine. All right. So of course, with high precision measurements, this will reveal important effect, which is the nuclear pattern distribution function, and which is interesting for our purpose of isobar studies for sure. Another thing which I would like to show you briefly is that not everything has B2. In particular, the Z B2 has been measured. No matter which entirety you are, B2 is consistent with 0. And the other thing which is particularly interesting is the W minus 2W plus ratio. This has been reported by Arthur's experiment with lead at 5 TeV, studied as a function of centrality. And this can be a really useful tool for tracking the neutron to proton ratios in centrality classes. The only disadvantage is that this requires really huge amount of statistics. This is related, this is like 0.5 inverse narrow bound. So maybe you will need something like 10, 20 inverse narrow bound to have an error bar, which is compatible with the size of the neutron skin effect. That's the colorless probe, and we can move on to colored probes, and those are the quark and gluons and the heavy quarks. I would like to give you a short introduction of why we are doing this in heavy ion collisions. That is because the QGP transport property, and also hopefully in the future, the structure can be studied with jets in general. So jets are a collection of partons which are penetrating through the medium originating from the process, and they can be receiving multiple soft scattering effects coming from the median and the jet constituent scattering. And usually we quantify the size of this effect by this so-called Q hat variable, the transfer momentum broadening squared per unit length to quantify the scattering power of the quark plasma. And of course, because of their scattering effect, so there must be median response to those scattered parton. And this can be seen from the experimental data as well. And because of those scattering, there must be also the holes which are propagating in the opposite direction of the parton propagation. And with a very precise understanding of all those effects, we hope we will be able to study the quark plasma internal structure with Modier scattering, which is we are not yet there, but we are making progress understanding the effects I illustrated above. And do we see jet quenching effect? The answer is yes. If you compare the event display in the left-hand side, which is coming from a proton-proton collision, you can see that initially the transverse momentum is conserved, right? So therefore you have back-to-back jets, while in the lateral collision from the event display, you only have one high ET jet. The other jet is somehow quenched and become energy flow over a wide range of phase space. And of course, we can quantify the size of this effect without using jet, which is what I'm going to do today, a charged particle RAA. And you can see that is a prominent S shape in the RAA as a function of transverse momentum. So what we are showing you here is a head-on collision, which means that I'm selecting very small centrality value 0 to 5%. And there's a very strong suppression of high-P particles seen also from this already very precise data set. The other thing I would like to point out is that it is interesting to look into the system size dependence of the suppression factor. So there are two figures here. The left-hand side are the tracks RAA with lower transverse momentum. The right-hand side is higher transverse momentum. In both figures, they are plotted as a function of number of participants. Right-hand side is central event. Left-hand side is the peripheral event. And you can see this RA value decrease as a function of N part in both low PT and high PT case. And interestingly, there are two collision systems taken at roughly the same center of mass energy. That is the xenon, which is shown as red, versus the blue, which is the lateral collisions. You can see interesting scaling behavior there. And that, yeah.
I don't understand. If that's jet quenching, then I think that would be more particles in the AA collisions. Why you sort of test them on?
Yeah, so the question was why we should expect more jets, right? So in the that is because when we define the nuclear modification factor, so we divide the jet yield by this N code. So therefore, of course, you have more jets initially, but because of this binary scale down the flow, so therefore, what we are doing is that if we normalize to a nuclear scattering level, then the jet is relatively more suppressed in the collision. I hope that clarified the question.
Just to also, because it also shifts your PT downwards. Too,
That's
right? So as you lose energy, what happens is that you don't have as many high PT particles, but you would have more low PT particles.
Yes, and that's yeah. So that give you this non-trivial result there. And the excitement is that we see there's a rough scaling behavior versus between xenon and lead, which we use this in the later studies for the isobar estimation. The other thing which we can look into is the anemoso anisotropy of the charged particles. I can divide the phase space into two pieces. The left-hand side is a low PT V2, and as you already learned, the majority of the workshop is actually on the pressure-driven expansion of the quark plasma, this flow signal, and that is shown in the left-hand side of this diagram. The excitement is that we also see V2 from high PT jets. And that is coming from the fact that it is harder to penetrate through a longer path length median compared to a shorter path length median. That is actually why it is producing so going through a different angle, the suppression factors due to jet functions are different. So therefore, you also leverage the V2 signal at high PT. So the interesting thing is that this we see a pretty tight correlation between the high PT V2 and the low PT V2 as shown here. There are two transverse momentum intervals. We collect the data from various of different centrality beams, and we see that they are essentially linearly correlated with each other. This linear correlation is telling us that the Hubble probes actually can see the quantum plasma shape. That is interesting. Keeping this in mind, we can ask a question, wait a second. So we have been studying those Hubble probes with high transverse momentum, and can we follow a very unique parton and see how this parton is thermalized inside the median? Maybe we get some more insights about what's going on. And that is exactly the purpose of having heavy quarks in the GAN. So Chang and Beauty quarks, they are produced before QGP formation. And once they are produced, the Chang and Beauty, in particular Beauty, cannot be destroyed by strong interaction. So they are just going to be floating around in the quark soup. And so this is a unique opportunity to study QGP with a slow moving Hubble probe. And you can see from here that essentially what happens is that those heavy quarks are kicked around by quasi-particles before they are hadronized. And the heavy so this means that the heavy quark diffusion can be a very useful way to quantify the immediate color force and also the transport property of the medium. And this is an illustration of how the heavy quark acquire the two. So at first, there should be no Nimuso anisotropy. And the interesting thing is that when this heavy quarks are propagated, really traveling through the median. So they interacting with the quantum plasma, and the QCD force is like wind you will be blowing those heavy quarks and increase the V2 of the Chang quark in the bass. And of course, this whole process can be modeled and be calculated in theoretical models. And at the very end phase of the process, of course, the Chang quark eventually have to hadronize, and you may also pick up some of the Nimuso anisotropy from the light flavor. And what we leverage is going to be this picture here. If we compare the charged hadrons, we will see that the Chang hadrons are moving toward the charged hadron V2, and those magnitudes can be correlated to each other. And let's take a look at what our data looks like. So this is comparison between the hadron and the D0 V2. So indeed, we see a positive V2 for the D0. This is a very interesting evidence for the Chang diffusion. And we see that the Chang V2 is smaller than hadron V2 in this figure. And also you can see that the Chang V2 is correlated with the hadron V2 reflect the initial.
So Yanji just
yes,
the hadron V2, the fraction of the baryon,
yes,
that region is not insignificant.
Yes, this is very important. Yeah, so of course, if you compare the pi plus pi minus, then you get the something more similar. But of course, that will be the detail for these.
So when you look at the definition of the V2 as a function of PT,
Yes,
it involves also a correlation between the flow angles for the hard particle and the soft particle.
yes.
So when you say they are correlated with hadrons, how does this angle correlation relate to that?
Yeah, I think the fact that if you only measure the V2 itself, and it's hard to infer this. So of course, we need to look into the higher order correlation and also the jet DV correlation, and you'll be able to really quantify those diffusions independently. Yeah, I think that's what we are trying to do. Okay, yeah, very, very interesting. Okay, very good. So the takeaway is the following. The colorless probe is modified, and it can be used to count the number of encode and the PDF. The color probe modify the size of the effect is correlated with soft particle observables. So these pictures bringing in already by Chen that the initial conditions changes how energy density and hydro evolution, and that create a carbon plasma of different medium properties. And in the theoretical model, we are using the median to calculate the expected jet quenching parameter Q hat and also the heavy quark diffusion, etc. So in some sense, they are connected to each other, but only indirectly. So what can we actually do in the next step would be in order to use hard probe as a sensitive probe for the initial conditions, we need to model and perform Bayesian analysis on both hard and soft observables simultaneously. And I believe this will be the next step. And I would like to point out that burning issues related to hard probes, initial energy density fluctuation changes the median we are really using for evaluating the quenching and the diffusion. The path length dependence of the immediate modification is different between different theoretical models. So that's actually related to quenching and the heavy quark diffusion mechanism. So just to illustrate the effect of the median, also the starting time of the median, etc. This is a work already a few years ago showing that if you use an optical Bragg model and the KLN initial conditions to produce the median, which roughly describe the two observables we see in the experimental data. They extracted the quark jet quenching parameter and differ significantly. Of course, there are false contribution from the initial state in the starting time of quantum plasma. And so this shows this is really something to be greatly improved so that we can understand the quark and the jet better. And the other thing is illustration of the heavy quark diffusion calculation. If you use a PHSD initial condition versus a Plato average initial condition, you can see as we introduced before, the Chang V2 is acquired during the process of evolution in the carbon plasma. The amount of acquired V2 is different if you use different median associated with different initial condition. So this is one of the major uncertainties so far, which is contributing to the heavy quark and jet quenching parameter calculation.
Yes. So when you use average, this is because the difference because one is event by event average, or this is more than that?
Yeah, so I think ideally you would like to use event by event initial condition, but it's not yet done in this specific work. So they just take a few 50 single and the average them. So you will have more bumpy structure compared to fully smooth PHS in the condition. And there's already this size of uncertainty. Yeah. Oh, if you use event by event, then you will be even more. That's the message.
If you use event by event, the difference will even be stronger, bigger.
Yeah, for sure. Yeah. Because this is already smooth, right? So,
yeah, but if you compare event by event PHSD, event by event Trento, it's not clear that
the problem is, yeah, of course, yes, of course, but PHSD have a much smoother initial condition, right? So,
even event by event.
I think so, yes. Okay, so so that illustrates the problem. So you can see if we use a model dependent translation of the jet quenching parameter in the heavy favor diffusion constant. Essentially, we arrive this picture here. So this is the eta OS extracted from soft probe, and largely they are consistent with each other, but the actual value differ by one order of magnitude. So essentially, we have no information. Why is this happening? That is because we have initial conditions and median variation that contribute in the speed spread. Underlying mechanism and halation effects not touched, but very important for the open heavy favor. And of course, the last thing is accuracy of the experimental data. And all those things can be improved along the way so that we can have a direct comparison between different probes. So for that, I think it's very important to look into different system size. I mean, will address many of the points which we have in the last slide. So different liquid flow measurements, fixing the intensity, but changing the system size can be extremely interesting. Model calculation shows that there's no there's a sizable effect still of a jet quenching effect in O and Agang, and also chunk diffusion can be studied in various of different systems in the same centrality. So this Jackie's paper showing that you can learn some more than system size can, and that will provide a stress test to lower all those theoretical uncertainties. Okay. So in the last 10 minutes, I will talk about the hard probes in Constraining and the zirconium collisions, and those are the preliminary results which we obtained 1-2 days
I thought you were listening to the talk. Yes, I thought you were listening to the talk.
We are working. All the time. So this is the calculation in the model. Sorry for the pronunciation, but essentially what we have been doing is to calculate the uncode as a function of centrality, and this could be the ratio of what we expect for Constraining and the coordinate. And the take-home message is that the unpart difference between these two systems is up to 6%, and the uncode is something like 9%. So this is roughly in line with what already shown by Wei Yao in the talk last week. And also we did the comparison between different uncode calculation using parameter sets shown here. You can see that they are splitting into two different camps, and that is because in the first three, these corresponding to the bottom rows, and you can see that the sigma p and the sigma n values are quite different compared to the first two data sets. So this shows us that for colorless probe, WZ and gamma EO ratios, those are sensitive to the uncode, will be a direct be sensitive to the sigma n and sigma p variables, and size of the effect is up to 8 to 10%. So of course, with the mindset we have given you in the first part of the talk, we were thinking about maybe we can use jet quenching and chunk diffusion to illustrate the difference, to figure out the difference between these two isobar nuclear structure. So therefore, what we have been doing is we use an unpart-based estimator using this scaling behavior and use this curve as a lookup table for the suppression factor. And then we take into account the slightly larger unpart in Constraining conditions compared to zirconium solution, collisions, and this will lead to a smaller RAA compared to the other system. So this effect is surprisingly small. Actually, in the end of the day, it's something like 1% level. And of course, this is for the LGC, and then we also did a study with a rig, and this is given by fitting the data from STAR and perform this part-based estimation. We can see that the size of the effect is also roughly in line, which is roughly 1% level. And this shoot up is related to the fact that we have measured problem with selection bias in the vertical event.
So this is under assumption that RE are the same, if in part are the same.
Yes, that's the assumption.
I think the effect that on the distribution itself is bigger because you have the same in part, you have bigger RA because the method distribution is different.
Yeah.
I think that's probably bigger.
Yeah, so that we can ask that question, and of course that's actually why we also have the calculation, direct calculation from triathlon model, which is this precedence event in the two systems left and right. You can see they're quite similar, and also there are information about the in and out of plane calculations also included that can be used to study the hydrogen too. And essentially, if we take the 0 to 10% star data for the calibration, which means that those dots are going to be exactly the same as the right-hand side dots. And we can predict what will happen in centrality dependence. And essentially what we see here is the following. So there are reasonable agreement, but the agreement becomes worse when we go to peripheral event. And that's associated with probably the selection bias effect. Since I don't really have a lot of time, so I'm going to move on, and we go ahead and calculate the ratio between different centrality, so different systems, and you can see that this IA ratio is something between 0. So the deviation is actually between 0 and 1.5%. And you can plot those things on top of each other, and you can see that essentially all those different methods agree quite well, showing that this estimation indication is somehow robust. And of course, we can also calculate the RAA as a N part and compare with star data. We can see very nice description here, but once we go to peripheral events, and then we cannot reproduce this downward trend from the theoretical models. And of course, the same story that IA ratio is of the 1.5% level up to now. I would like to also give you some feedback on the the implication of this result. So the modification or say the IA ratio is so small, and that is actually a good thing. This means that the jet quenching effect is actually canceled almost perfect, up to 1% level. So this means that if we just look into the yield ratio, this will be a much more powerful way to reveal the initial condition. So RAA, as we all know, makes a theoretical uncertainty and P3 reference uncertainties in. And instead of the RAA ratio, we should really look into the yield ratio. They are much more sensitive to initial condition by alcohol. So
why there's still PP reference uncertainty for RA ratio?
Because
You mean RA?
because this is RA, right? So,
But you want to take the RA ratio that. So is RA ratio
no. I'm saying the IA itself is not a good thing. And RA ratio, of course, you can cancel out the PP reference.
Number collision is different.
Yeah, but this is still bad because you mix it with the yeah. Okay. So I almost done. So the point is that we should just look into the VO ratio, and this is really a very good news because we have also calculated the yield ratio for the hard probe, and this is a picture. So we have two different lines showing here. The solid line is the calculation, and this part based method very simple-minded, as is also shown here as dotted lines. And you can see if we look into this different parameter set, we have really a sizable deviation from one, which is really intriguing. And also, first of all, this is very similar to electroweak probe, but we rely on cancellation of the median effect. Okay, really cute. And secondly, this will require much smaller statistics compared to Z and W naught, which are not accessible for star, and higher accuracy than isolated photons. So this is really a very interesting development. Finally, you can see based on what we have learned so far from the last 2-3 days, there's this difference between these two models and the N part. So that roughly tells you where you have to start to be very, very careful about your selection bias. And that is around 40 to 70%. So I think that's something which we should keep in mind when we do the experimental extraction of the ratio and also compared to certain calculations. All right, so this is a summary. So I hope I have convinced you that colorless probe that are modified in KBM collision sensitive to ENCO and the PDF. Color probe modified the size of the effect reflect the initial condition of the collisions. We really need comprehensive studies of different collision systems and to bring down many theoretical uncertainties. Work during the workshop, WZ gamma, and yields ratios, they are direct window to ENCO ratios. they are sensitive to sigma P and sigma N, and also potentially sensitive to neutral skin if we have very, very high statistics, much greater than 10 inverse nanobond per system. Difference in the jet quenching effect is largely cancelled at the level of 1 to 2%. This can be extracted by hadron to electroweak boson yield. So if we really want to see the jet quenching effect difference, we should do this so that we are moderately independent. Quenching effect is largely canceling a yield ratio. That's a great news because this means that we should use high PT jet and hadrons as information to further reconstruct it. That's all. Thank you very much.
You showed this strong correlation between the high PTV2 and the low PTV2 in lead.
Yes.
Has this been looked at in PLED as well?
Yeah, so this correlation doesn't really work, right? So in PLED, right? So we don't really have any sizable indication. So that's interesting. Yeah. And why is happening? And the other thing is that the proton lab measurements, this IAA or say equivalent of that require a lot of intervention experimentally and theoretically. I'm not sure they are in the same level as a reliable measurement compared to that. Yeah. So in short, we don't know. Yeah.
I think I'm quite not surprised by what you're saying that this correlation goes away in PA because there, everything flow direction, it's controlled by fluctuation, by geometry.
Yeah, but the high peak could be the same fluctuating jump.
Yeah, but the thing is that experimentally, what I want to say is that experimentally we just don't have the sensitivity to your MC. So that's actually why I say don't know.
I think the mind of data is that you need to do non-flow subtraction before you can do it. You can build this correlation. That subtraction itself is kind of, you want to go to 20 GeV for PLED and now we do and subtraction is a big thing.
And selection bias.
Yeah.
Selection bias basically kill the measurement.
There are more questions? I want to ask a question. Can you do this make a prediction for large hadron collider energy? This is for the star for the weak energy, right?
No, we have both energies, right? So
Which
it's,
one?
so it's too small, so 5 TeV and 200 GeV. And
Okay.
project calculation is being done by Wilkett, and you will see much more results.
No,
next
but the 5 TeV you calculate low PT, right? I mean, I'm talking about.
Oh, you mean the high PT?
Yeah.
Yeah, I mean,
Well, that.
yes, we have the calculation, but it's not shown. But essentially, this effect is even smaller.
Oh.
So it's pretty obvious, right? Because the RAA is essentially larger. So therefore suppression is smaller. So this effect is even smaller. Yeah.
There you're mixing flow effect. There's still some. Low PT and 5 TeV.
Yes.
There are lots of
Yeah.
flow effect.
Yeah, of course. But what I'm to say is that at high PT, the same argument still works, and the difference will be even smaller.
Oh, there's one question. Yeah, go ahead.
For the Jacobian and Lucinium, do you separate like H plus and H minus to see if they are different? In principle, the leading charge should be different, right? Between Jacobian and Lucinium.
Yeah. And that's what we also discussed, but I think within the framework, we cannot do it there are no fragmentation function. In the
You
model.
mean the UD quark unit, you treat them always the same?
Yeah, so that's actually why we show only the hadron as magnets.
Is there a measurement that shows the H plus over H minus ratio? Yeah, it's a lot.
Well, probably showed, Chris showed something, right? That low PT,
But
Chris
if you calculate there is a sensitivity, I think people will look for it, right? I mean, we know a high PT, high plus, high minus, and FRP are different.
Okay,
It is not.
one more question is You talk about the partner dependent of Jack Quentin.
Yeah.
What is the evidence so far? Directly, do you directly observe the partners, the dependence L square versus L, like, this different power of the L? Partner, do you see this quadratic versus linear?
Yeah, that's a major uncertainty, right? So you can dial up and down your, the Q hat value, right? So that's actually why a stress test would be very useful, right? So right now, there are many different spherical models. They have different pathless dependence, including different pockets, even long versus weak. And the problem is that if you dial up and down the Q hat, then you can roughly reproduce the head.
But I thought the V2 is much more sensitive to the partners.
Yes, but you have enough. Yeah, that's exactly what I was saying, right? So you can change the starting time of the clock on plasma. Then everything is washed out. So bad situation, and we need to solve this.
I mean, you don't have like a Bayesian analysis, but soft control.
Exactly. That's what I was trying to say, right? So you have to put all those models in the parameter space, and you need some dependency to constrain both.
I mean, they have it for RA, but for V2, you need a huge number of events, so like
It's not yet.
statistically, this would be very, very difficult, because the jet goes slow ever beyond this.
But there's a clear path forward. Yeah, that's good.
Okay. But we have few minutes left. Are there more questions? Okay. If
So
not,
I'm just following up on my question, what I'm thinking is for the if in the neutron skin, if it has more D quarks than U quarks,
Yeah, yeah.
right? So
Yeah.
it will be, you should
I
see
understand
a
that.
different quenching effect.
Yeah, I think we were talking about this, right? So is there a replacement for W minus over W plus in the family? Maybe some high PT particle charge can be helpful. I don't know.
But
We haven't tried.
At least W for W and
There's
C
nothing
probably
there,
is a
right?
hopeless.
Yeah, that's why we propose, at least you can be sensitive to the call with high PT particle, which is quite clear. Yeah.
okay. So let's thank ING for this nice talk.